So we're going to look at a second video based on disorder and entropy. We recognize that entropy is a state variable. We've had some experience with state variables and thermodynamics laws. For instance, here's a state review of thermodynamics. The 0th law was our law to define temperature, and that is indeed a state variable defined with either macroscopic or microscopic ideas of the system. The first law dealt with energy. We had that the change in internal energy was related to the transfer of energy into a system, either by heat or work, and that was our first law of thermodynamics. So that definitely is dealing with energy, in particular conservation of energy. The second law we've defined as dealing with disorder or entropy, and we define that with the letter S as our variable. There's a third law, which we're not going to go into in this course. This is just a survey course to introduce this topic, but if we did talk about the third law, it is a law that describes what happens as we approach absolute zero. So as the temperature approaches absolute zero, the internal energy of the system approaches absolute zero, or approaches zero, and the value of our entropy in that case approaches a minimum value. So we can see where all these laws are leading. They're all describing states of a system, and they're all defined by state variables that describe just the system in that moment. We can see this being our 8th lecture and our last lecture on entropy. We can see some premonition about what's about to come, because we have a temperature, energy, entropy, temperature again, TEST, or you might expect after this a test coming up. So after this 8th video is your first test. There is a 4th law I just want to mention at this moment. Very not well known, the Golben law, designated by G, kind of goes something like this. If everyone sent me $1, I would be rich. I think everybody should abide by this law. It is a law with no exception in the universe. All right. I cannot be bribed. Don't send me money. I don't need money. Please disregard this 4th law. The point is, by state variable, these variables depend on the present thermodynamic state of the system and not necessarily on the path that brought it to that state. So the state is the state. We don't worry about how it transferred from one state to the other. It's just these are variables that describe the state at that moment. Keep that in mind. We defined entropy in the last lecture, and we said it was a measure of disorder. And we said that in all real processes in the universe, the entropy of the universe will increase as that process proceeds. So we can actually look at 2 moments of time and in the universe, and whatever moment has the greater disorder came at the later time. So we can see that a process proceeds in a certain direction based on the value of entropy as it goes from one state to another. In this lecture, we wish to try to measure that both in a statistical way and in a thermodynamic way. To do this, we're going to define what we call microstates and macrostates. Statistical mechanics will conclude that isolated states tend toward disorder. If you have an isolated state, over time it will become more disordered. And entropy is a natural measure of this process of disorder. What does this really mean? To understand this, we define macro and microscopically states. A macrostate is a description using macroscopic variables such as pressure, density, and temperature, something that can describe the whole system at once in that system. A microstate could be like a snapshot of that macrostate at any particular configuration. So you have all your individual constituents wherever they happen to be, and that would be our microstate, which is a specific subset of what the whole state could be doing over time. So a microstate is one particular configuration of the full macrostate. For any given macrostate, a number of microstates are possible. And it's found that is assumed that all microstates are equally probable. So any snapshot of a macrostate at any particular moment will have a microstate, and that is equally probable with any other microstate that it might have. Keep that in mind as well. When all possible macrostates are examined, it is found that macrostates associated with disorder have far more microstates than those associated with order. In other words, one way to define disorder is the fact that you have more possibilities of what your state could be. And so you have more microstates. As you add more microstates to your possibility, then those are the possibilities you can go through, as opposed to an ordered state, which has fewer microstates, less possibilities to deviate from one particular look or one particular configuration. The probability of a system moving in time from an ordered macrostate to a disordered macrostate is far greater than the probability of the reverse. This is because there are more microstates in a disordered macrostate. So, you have a macrostate, all possibilities of microstates equally probable, but as you go to more disorder, there are more microstates, more possibilities, and more of a probability that you will be in a disordered state. If we consider the system and its surroundings to include the universe is always moving toward a macrostate corresponding to greater disorder. So as time progresses, as the universe expands, there are more possibilities of microstates, and hence there is more disorder because there are more microstates. This might be confusing, so let's look at an example. We're playing poker, and you've just been dealt a 5-card hand. And here are two possibilities. The hand on the left is a crummy hand. It's got a mixture of suits, and the numbers are such that you really can't do anything with them. Even if you were to give 2 cards in and get 2 cards from the dealer, there's no way that you could construct a straight from this hand because of the separation of the cards. And even if you got exchanged suit cards from the dealer, there's no way you could even construct a flush from this hand. So it's really pretty crummy. There's not even a pair in there. Right now it's just queen high. It's a crummy hand. So we'll label it crummy hand on the left. On the right, you've got a straight already. It's not only a straight, it is a royal straight, so it's the highest straight you can possibly get. Beats all other straights because it's ace high. And it's got all of the same suit. It's all spade suit. So it's a flush as well. And those are the 2 highest configurations you can get, even better than 4 of a kind. So this is the best hand you can possibly get, at least in spades. And so this is a royal flush. All right, so you've been dealt 5 cards, and the probability of gaining any particular hand in poker, as you're being dealt 5 cards, well, the first card is 1 in 52 cards. And then, since you've already taken that card, your second possibility would be 1 in 51 cards. And once you get that card, your third possibility would be 1 in 50 cards. And the next one would be 49, the next one would be 48. So, for your 5 cards, the probability of you gaining any particular hand would be 52 times 51 times 50 times 49 times 48. And I've calculated that out, and that is a little bit more than 311 million possibilities for your hand. So this particular crummy hand is 1 in 311 million, And same thing of possibility of getting a nice spade royal flush on the right, 1 in 311 million. So the probability of getting this crummy hand as opposed to this royal flush is the same, 1 in 311 million possibilities. However, there are a lot more other crummy hands out there. Maybe not just these 5 cards, but you can switch up the suits and switch up the numbers and still get a lot of crummy hands. So if we define what we call a macrostate, called a crummy hand, there are a lot of microstates associated with 5 different cards you can get for each microstate. And so there are a lot of microstates that could comprise a macrostate of a crummy hand, as opposed to a royal flush macrostate, which only has these 5 cards. And so it only has one microstate associated with this spade royal flush. So it's much more likely you're going to get crummy hand as opposed to a royal flush, a spade royal flush, because there's more microstates associated with a crummy hand as opposed to the one microstate associated with the royal flush macrostate. So the probability of any crummy hand is much, much greater than the probability of a spade royal flush. You know, millions of crummy hands, 1 out of 311 million hands would give you a spade royal flush. So that's one example. Let's try the marble example. Suppose you have a bag with 50 red marbles and 50 green marbles. You draw a marble, record its color, return it to the bag, and draw another. So you get a bag, any old bag, and you reach in, pull out a marble, and first marble you pull out, let's see, red marble. So you pull out a red marble. Alright, so I don't have a red marble, but let's pretend this was a red marble. So you pull it out and put it back in. Could be either green or red, so probably the probability of picking out a green or a red is 50 and 100 or 50%. So you go in there and you pull out the next one and you pull out a green one. So that probability was 1 in 2. And you keep on pulling out marbles, and the next time you pull out a marble, or you put them all back in, anytime you pull out a marble, there's a 1 in 2 chance of it being red and 1 in 2 chance of it being green. Next time you pull it out, you get a red one. Okay, all right. Put that one back. What's the chances of you getting a green one? Still 1 in 2, and same thing for a red. So you go in there and pull it out, and you get a red. Okay, so you got red, green, red, red. This particular microstate is that. Red, green, red, red. It is a subset of the macrostate that would be 3 reds and 1 green. So that macrostate could have 4 different configurations. You could have the green first, green second, green third, green fourth. 4 different configurations of 3 reds and 1 green. And this is one particular microstate of that macrostate. For picking 4 marbles, what are all the possibilities? What are the possibilities of macrostates, and what are their particular probabilities? Let's take a look at that. Here's a graph, and here are possible macrostates on the side here, and possible microstates in the middle. And we can see that if we consider all the possibilities of us pulling out 4 marbles, that there are 16 possible microstates altogether. 2 to the 4th power. So either red or green on the first one, red or green on the second one, red or green on the third one, red or green on the 4th one. 2 to the 4th power, 16 possibilities. If you got red, 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 that's 1 out of 16 possible. If you got green, 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 that's 1 out of 16 possible. So for the macrostate, which we might say is 4 reds, you have a microstate of 1 out of a possible 16. The probability of that would be 1/16 or 6.3%. And the probability of getting a nice ordered 4 greens would also be 1 out of 16 or 6.3%. Interestingly enough, to get 2 reds and 2 greens, 2 of each, there's only 6 macrostates out of the total possibility of 16. 6 out of 16 is 37.5%, not 50%, 37.5%. So argue with the mathematicians on this. But there's only 6 microstates associated with that macrostate of a possible 16. We can see basically on this, though, that the more ordered states, like all red or all green, are less probable, 6.3%, as opposed to the more disordered state, like 2 red and 2 green, which is 37.5%, much more, 6 times more probable. So the most ordered states are the least likely, the most disordered states are the most likely, and hence we're most likely to have a macrostate that, in this case, that would be disordered as opposed to a macrostate that was more ordered. And this is a very small example where you only have 4 selections here, but if you look at any kind of more complicated system, maybe like a gas in a room or something like that, there are infinite possibilities, all of them increasing the number of microstates that you possibly can have and the possibility of more disorder. One way of looking at entropy in a thermodynamic way is the study of the transfer of heat. Transfer of heat is going to change your system or change the value of entropy. And so we define entropy based on that. We're going to let our infinitesimal transfer of heat in a reversible system be the amount of energy transferred by heat when we follow a reversible path. This infinitesimal change in entropy, ds, is defined to be this infinitesimal change in heat in a reversible path over the temperature T. This change in entropy will only depend on the endpoints because entropy is a state variable, and so it will be independent of the path that actually followed between those 2 states. Entropy is a state variable. Once we calculate our change in entropy, that is a value intrinsic to that change in states. So we're going to measure our change, our heat exchange, our heat transfer along a reversible path. Even though the system may have actually followed an irreversible path, it doesn't matter. How it got there between the states doesn't matter. We're going to choose the reversible path quasi-statically as it goes from point to point, so the path itself is not responsible for the change in entropy. It's not increasing the number of microstates, if you will, increasing our disorder in that sense. So we choose a reversible path because that is the best possible path for our change in entropy. We're free to choose a particular reversible path to evaluate the energy between any 2 states because entropy is a state variable. Actual path doesn't matter. Hence, for a finite process, we define our change in entropy as being the integral from initial to final of the infinitesimal change in entropy, the integration of our change of heat transfer along a reversible path relate to temperature. Let's try an example. A 70 kilogram log falls from a height of 25 meters into a lake. If the log, the lake, and the air are all at 300 Kelvin, find the change in entropy of the universe for this process. Based on what we've defined for a thermodynamic value of entropy, we want to figure out how much energy is involved in the log falling. We're going to assume that all this mechanical energy of the log falling is going to be transferred into heat into the system. So all of our potential energy is going to be converted to heat. So our heat is going to equal mgh, 70 kilograms, 9.8, 25 meters. That's going to be 1.72 times 10 to the 4 joules. That will be our total heat exchange in this case. And it's all done isothermally at 300 Kelvin. So our entropy change is going to be this heat over that temperature. 1.72 times 10 to the 4 joules over 300 Kelvin, 57.2 joules per Kelvin. And that's a positive value, so we have gone towards more disorder. This is a process that possibly could actually take place. The change in entropy for a phase change is the heat associated with that phase change at the temperature at which the phase change takes place. So it's an isothermal process. We can prove this. We're going to involve the heat of the phase change itself, either the latent heat of fusion or the latent heat of vaporization, depending on which phase change we're going through, solid to liquid or liquid to gas. So we say our change in entropy is from initial to final, our change upon a reversible path of the heat transfer at that temperature. In this case, we're at a constant temperature, so we can take that out of the integral. So we have 1 over T times the integral of our heat exchange, and that is just the heat of our reversible process, in this case the phase change at the temperature that we're doing this. Our phase change is the mass times the latent heat. Here I got it for fusion, but it could be the mass times the latent heat of vaporization as well over that temperature that the phase change occurs. So that's a simple derivation of the change in entropy for a phase change. Let's try this out on a problem, number 19 in the problem set. 500 grams of ice is melted at a temperature of 32 degrees Fahrenheit. What is the change in entropy in joules per Kelvin? As we do all these entropy problems, we want to make sure that all of our temperatures that we use are Kelvin. We have to use Kelvin because that's our absolute scale, starting from 0 and going up. There's no negatives in the Kelvin scale, and we need to use that scale for these kinds of problems, unless it were a change in temperature involved. So our temperature in this case is the temperature in Celsius plus 273 at 32 degrees. We're at 0 degrees Celsius. So our temperature in Kelvin is 273 K. We're going to go through a phase change, so that is the mass times the latent heat of fusion for water. The mass was 500 grams or 0.5 kilograms. Latent heat of fusion is 3.33 times 10 to the 5 joules. And we're going to do it at 273 Kelvin. So we're going to have a change in entropy for this process of 610 joules per Kelvin. What about a reversible cycle? For a reversible cycle where you can go from one state to another and reverse yourself, there should be no change in entropy if it's reversible. As you're going from state to state and there's no consequence of that, then no change in entropy. And we can prove this. Consider, for instance, a Carnot engine. By definition of our change in entropy, the change in entropy should be our heat exchange from the hot reservoir at the hot reservoir temperature minus what we lose to the cold reservoir over that temperature. So it's QH over TH minus QC over TC. That should be our change in entropy, these two exchanges that take place at the two places in our Carnot cycle. But we also know for a Carnot cycle that the ratio of the heat transfer at our cold reservoir to our hot reservoir is also equal to the ratio of the temperature at our cold reservoir to the temperature at our hot reservoir. So Q sub C over Q sub H equals T sub C over T sub H. Since these ratios are equal, I can take the first term of this expression at the top here and multiply it by the left-hand side of this equation here. And I can take the right-hand side of this equation and multiply that at the top here. So I'm basically multiplying both of these terms in the change in entropy by the same quantity and see what we get. Knocking out the Q sub H and knocking out the T sub C, we see that the first term is Q sub C over T sub H, and the second term is Q sub C over T sub H. They are the same magnitude terms, so one minus the other will give us a change in entropy of 0. So for the Carnot cycle, we have proven that the change in entropy is 0. And that is a reversible cycle. It has two adiabatic legs and two isothermal legs. So it's truly a total cycle that is reversible. Since we have done this for a reversible cycle, a Carnot cycle, we have proven in essence that this is true for any reversible cycle. S is a state variable, so it doesn't really matter how we get from state to state. Reversible is the way to go. And so this is true that the change in entropy for any reversible cycle is the same as the change in entropy for a Carnot cycle, which is indeed 0. So delta S is 0 for a reversible cycle. What about the change in entropy for thermal conduction? Let's say you had a hot and cold interface, and there's going to be heat exchange from the hot to the cold. What is our change in entropy then? Well, the cold reservoir will absorb our heat transfer, and its entropy will increase by the heat it absorbs over the temperature of the cold reservoir. Same time, the hot reservoir will lose that same amount of heat, and its entropy will, its change in entropy will actually go down as we're losing that heat. So that's something that's going to it's going to happen in that transfer. If we add these two, we'll find our total change in entropy. And since the temperature of the hot reservoir is greater than the temperature of the cold reservoir, this second delta S is going to be a smaller quantity on the negative side than the first delta S, because T sub C is going to be a smaller number. And so if we add these two changes in entropy, we are going to get a positive quantity, which means that this is a process ultimately that will take place in the universe. We will have a heat exchange from hot to cold, because our total change in entropy will be a quantity that is greater than 0. As the reverse is not possible, to go from cold to hot, we would have to have a heat exchange where it's more negative on the first end and then less positive. So as we're going into the hot reservoir, and our change in entropy in that case would be negative, which is not possible. So the way it happens in nature spontaneously is heat flows from hot to cold, not the other way around, and we prove it using the concept of entropy. What about an isothermal process? An isothermal process, both are heat transfer upon a reversible path, and our temperature only depend on temperature, and that indeed for isothermal process is constant. So our change in entropy is equal to, say if we choose an ideal gas, nRT dV over V. That's going to be our change in heat, as we've proven earlier in an earlier chapter. And multiply that by 1 over the temperature. The temperatures cancel out. And then R constants. So we're going to have dV over V integrated from initial to final. And we end up with the number of moles times our gas constant, natural log, final volume over initial volume. And that is our change in entropy for an isothermal process as we go to a final volume as opposed to an initial volume. What about an adiabatic free expansion? An adiabatic free expansion might be, say I have some kind of isolated container insulated from the external world so there can be no heat exchange into this container. And I've got a gas confined to half of that container with a membrane, and then I destroy the membrane or pull it out and allow that gas to expand freely into the rest of the container. So that's going to be a process that will happen, and it will gain more disorder, and it's not likely it's going to go the other way. You know, as I fill into that vacuum, that void, the molecules will then fill that void and stay there, and it won't actually move in the opposite direction at any point. How can I prove that? Well, let's consider this. We're going to have no heat exchange in this case. We can't use a heat exchange because we have an adiabatic system, so there is no heat exchange. However, we are going to change our states. The no heat exchange is an irreversible process, but we could use a reversible process between our initial state and our final state. Namely, we could think about the isothermal process between these two states, which indeed would be a reversible process. And we just proved, as we have a change in volume for an isothermal process, that the change in entropy is NR, natural log, final volume over initial volume. So even though the isothermal process is not the process here, being a reversible process, it can describe the change of states from one state to another, and hence we can use this for an adiabatic free expansion. In this particular case, as it's freely expanding, the final volume is going to be greater than the initial volume, so the natural log of that fraction is going to be a positive quantity, and our change in entropy then will be a positive quantity, and hence it's likely that this process will occur where the molecules actually expand into the void, whereas the reverse, having a smaller volume as opposed to the larger volume, is a process that won't occur because that will give us a negative entropy on the whole. So in case entropy and the disorder of the gas increase as a result of the irreversible adiabatic free expansion. What about the change in entropy associated with a substance's change in temperature? Well, let's consider a change in temperature of a substance. The heat exchange is equal to mc delta T, as we've shown earlier when we were discussing heat. So our infinitesimal heat along a reversible path will be mc, infinitesimal change in temperature. As we integrate this over a temperature change, in this case T is a variable of this entropy change, M and C are constants, take that out of the integral, so we'll integrate from initial to final of dt over T, and that indeed is just the natural log of that. So we have mc natural log T final over T initial, and that is the entropy change of heating a substance from initial temperature to a final temperature with the specific heat of little c. If the substance is a gas and the temperature variables are not given, then you could use the ideal gas law to find the ratios of the other variables. In other words, we know that PV over T is a constant. P initial over V initial over T initial is equal to P final, V final over T final, and hence we could find the ratio of T final over T initial and express it as either a ratio of pressures, volumes, or both, and substitute that into this expression and calculate the change in entropy that way, if that happens to be the variables that we are given in the problem. Take a look at the problem set and example problems and how they're solved online using educreations to see how this might work out. So summary of change in entropy for this chapter. Isothermal heating or adiabatic free expansion, our change in entropy is N, number of moles, gas constant R, natural log final volume over initial volume. For conduction from a temperature reservoir, change in entropy is the heat exchange or the temperature of that reservoir. If you go from a hot to cold, you're going to have to add and subtract based on whether the heat's coming in as an addition or heat going out as a negative, and add those together to get your net change in entropy for that process. For isothermal phase change, It's the heat associated with the phase change, mass times the latent heat, over the temperature where that phase change occurs. Everything in Kelvin, make sure everything's in Kelvin. Heating a substance with an associated change in temperature, delta T. That is the mass times the specific heat of that substance, natural log final temperature over initial temperature. Heating a molar gas with an associated change in temperature. Note that our molar gas, molar heat, or molar specific heat is either the molar specific heat at constant volume or at constant pressure. We didn't derive this, but it's the same kind of derivation that we use for heating a substance with a change in temperature as well. And that is the number of moles times the molar specific heat times the natural log of our final temperature over our initial temperature. So same kind of integration that we would have to derive that expression. And finally, for a reversible process, the change in entropy is 0. So these are formulas. You might want to put this on your formula card for the tests or quizzes. And take a look at the example problems in this chapter, work those out and look at those examples, and get ready for your first test. Good luck.